Greetings YouTubers, I'm Rick the Tech Enthusiast here with the next Elegoo lesson number 24, 8 LED with 74HC595, or simply the 74HC595 shift register. In this lesson, we'll cover the 74HC595 shift register IC provided in the kit and run a sketch provided with the tutorial to demonstrate the functionality. Then I'll expand this sketch by connecting two shift registers together. So let's start building. The 74HC595 shift register integrated circuit can be used to add additional output pins to your Arduino projects. It only takes 3 Arduino pins to control 8 74HC595 output pins. And if you connect them back to back, or the output from one to the input of the other, the Arduino UNO can control up to 4 74HC595 shift registers chained together. The HC74595 integrated circuit has an 8-bit serial input and both a serial and parallel output with latching. Input is handled using pins DS, SH_CP pin, or the shift register clock, and the ST_CP pin, or the latch clock. Other pins are the output enabled pin, master reset, the serial output pin, 8 parallel outputs, and of course power and ground. During normal operation, the output enabled pin is connected to ground and master reset is connected to 5 volts. Simply, the 74HC595's register is a flip-flop with another flip-flop for the latching output. Typically, before accepting a register value, the latching clock is set low to freeze the output and make it ready to receive new input. When a signal is applied to the D input, the rising edge of the register's clock enables the flip-flop to store the D value and output that value to Q. That output value becomes the input to the latching flip-flop. The rising edge of the latching clock enables the latching flip-flop to store and output the value on its Q, which is connected to an output buffer. Here you can see that the output buffer is enabled or disabled based on the output enabled value, which is also inverted. The output enabled value needs to be held low so that the inverter's output remains high and allows the output buffer circuit to operate. One can also see that the master reset value works on the same principle, except it must be held high so the output value of its inverter is low and it doesn't reset the register's flip-flop. Here's a sample of the 74HC595 shift register logic diagram. It works using 8 flip-flops chained together to accept the serial input with 8 flip-flops to the latching output. Like before, the first step is to set the STCP or latch clock pin to low to hold or latch the output. This prevents any changes to the shift registers from showing up on the output. Serial values are then sent to the DS pin, and as the rising edge of the SHCP pin or the shift register clock goes high, it toggles all the flip-flops to accept and hold values from either the DS pin or the previous flip-flops. At the same time, the output from the last shift register is sent to the serial output pin Q7'. This is repeated 8 times until all the bit values are stored in the shift registers. Once completed, the STCP pin or the latch clock pin is set high, and the rising edge triggers all latching flip-flops to accept and hold the outputs from all the shift registers. These are the output values for pins Q0 through Q7. The tutorial and the datasheet have additional information on the 74HC595, so it's a good idea to take a look at them. For this lesson, you'll need the following items from your kit: the Elegoo UNO R3 board, 74HC595 shift register IC, 8 LEDs 2 blue, 2 yellow, 2 red, and 2 green. 8 220 ohm resistors. The breadboard. And a bunch of male-to-male jumper wires. I think about 13, but now I also have a bunch of these short little pre-cut wires, so your mileage may vary. On page 164, you'll see the following schematic. And here's my revised schematic. The DS pin is connected to D12. ST_CP pin is connected to pin D11. SH_CP pin is connected to pin D9. Master reset pin and VCC are connected to 5 volts. The output enabled pin and ground are connected to ground. Q0 through Q7 are connected to the LEDs through the 220 ohm resistors, with the cathodes connected to ground. On page 165, you'll see the wiring diagram, and here's my revised layout. I tried to route the lines from D9, D11, and D12 from the Arduino to the breadboard without crossing the integrated circuit. I did this by using 2 available 5-volt and ground rails on the breadboard. On page 168, there's a photo, and here's my photo. As before, the little pre-made jumper wires help keep things neat. Okay, let's move on to the code. As before, we'll load the recommended sketch provided in the tutorial. Go to the File menu item. Select Open, and browse to where you saved your Elegoo files. Then under your language, Code, under Lesson 24, 8 LED with 74HC595, under 8_LED with 74HC595 _flash_LED. Whew, that was long. And open the 8_LED with 74HC595 _flash_LED.ino file. That was long. This sketch starts with the global variables to set the delay time between the LED changes. The ST_CP latch clock is set to pin 11. The SH_CP shift register clock is set to pin 9. Serial data pin is set to pin 12. And lastly, a byte LEDs variable is set to 0. But it might be better to imagine that the value is set to a binary value 0000000. That way we can visually see all 8 bits. The void update shift register starts by setting the latch pin low. This freezes the output. Shift out is a built-in Arduino function that sends the byte LEDs 1 bit at a time to the serial data pin using the shift register clock pin. Shift out function requires the bit order parameter. Bit order sets which order to shift out the bits, either using the most significant bit first, MSB FIRST, or least significant bit first, LSB FIRST. The sketch uses the least significant bit first. After that is done, the digital write sets the latch clock pin to high, setting all the latch outputs to the new values. Void setup defines the pin modes for the latch clock pin, data serial pin, and shift register clock pin to the output. Void loop starts by setting the byte LEDs to 0. Remember, this could be written as 0B for binary, 000 00000. There should be 8 zeros there. Then it calls the function update shift register, which will send the 8 0 bits to the shift register and pins Q0 through Q7. A small delay is defined by D delay. A for loop loops through the I values from 0 to less than 8. The built-in function bitSet sets the individual bit at location I in the byte LEDs to 1 or high. The call to function update shift register will then send the new value of LEDs to the shift register IC, turning on the LED that corresponds to that bit which was set to 1. A small delay occurs and it repeats for all 8 bits in the byte. Then it simply loops. So as you can see here, we have the shift register right there, and the output lines are all going to the 220 ohm resistors and all the LEDs. The output of Q0 is routed around to this pin. So that's these little jumpers are used for. That's what these little jumpers are used for. Here we have the DS going to pin 12, and we have the STCP, or the latching clock pin, going to D11, and then we have the SH_CP pin, which is a shift register clock pin, going to D9. And then there's just power and ground. Here we have a little jumper, if you can just barely see it, it goes to the BCC pin, and then we have the ground jumper right here to this rail for the OE pin, and the master reset is to +5 volts. You can see how we just go from, looks like this is this is LED 7, so it goes from 7 to 0, and just sequential turning on all the LEDs one at a time through those bits, and then resetting those bits. Pretty simple. You can see it's a pretty simple circuit. Not too bad. I like it. That was a pretty good example sketch, but let's demonstrate how the serial output for one shift register would work back to back with another shift register. Here's my revised wiring diagram. Notice that it's basically the same as before, but there's an additional 74HC595 shift register, 8 more LEDs, and 8 more resistors. The serial output of the shift register 1 is the input of shift register 2. The clocks are shared between both. Here's the new wiring diagram. I grouped the LEDs all to one side and the shift registers to the other. The power and ground rails make it easy to add additional components. Let's check out the code. Here's my revised sketch. This sketch demonstrates how back-to-back shift registers could work. The trick is that we need 16 bits to store the LED locations. I've also added a circuit diagram in the sketch's top comment area for anyone who's casually reading this code. Moving on, we'll have the same global constants that were used in the previous sketch. I've added a new global variable, direction state, as a Boolean. This will be used to set the direction of the LEDs. The void update shift register function was modified to handle an unsigned 16-bit integer. The variable LEDs is now passed as a parameter rather than being a global variable. There's also an optional Boolean isMSB first parameter, which defaults to true. Looking at the variable LEDs, and if you think about it, an unsigned 16-bit integer is really like 2 bytes or 2 8-bit values concatenated together. A 16-bit value can also be called a word, which brings us to the 2 new local byte variables, low LED and high LED. They are set to the low byte and high byte of the 16-bit word. Shifting the values 8 places could also have been used here, but it was a neat way to introduce these built-in Arduino functions. As before, the latch clock pin is set to low to freeze the output latch values. Here, the if statement will check the direction is MSB first to switch between the shift out functions using the least significant bit first or the most significant bit first. Regardless, the next step is to use the shift out function, which can only handle a byte value. This was the reason I broke up the LED's value into a low and high bytes using the low byte and high byte functions. Again, I could have simply shifted the bits 8 places, but I thought this was a neater way. Lastly, the latch clock pin is set high to accept the new output values. The void setup remains the same as before. We set the pin modes for the latch clock, serial data, and register clock pins to output. The void loop starts with a local variable LEDs, which is set to binary 0. I'm showing it as a 16-bit binary to illustrate that each bit represents an LED. This time we have 16 bits. To clear the LEDs, the update shift register function is called, passing the parameter LEDs. Then we have a small delay. Like before, the for loop is used to increment through all the LED positions. This time we have 16 LEDs, 0 through 15. Each time LEDs is reset back to 0. That way we only turn on one LED at a time. The bit set function sets a single bit to 1 depending on the I position and is saved back to the variable LEDs. The function update shift register is called, passing the new LED's value and direction state, which should turn on the LEDs corresponding to the bit values set to 1. In this case, just one LED will turn on. There's a small delay and then it loops. When the for loop is completed, the direction state is set to the opposite value so that the next time the direction is changed. Simple. Let's upload the code and check it out. So as you can see, I have the shift register here, the original one, and the one I added. You can see the jumpers for the clock and latch have been jumpered over to the second shift register. The DS is coming over and to the first register, and the output of that register is going to the DS of the second register. These blue lines show the outputs of the second register, and these yellow lines, the yellow wires, are going for the outputs of the first register. Then they're just power and ground. So what's happening here, as you can see, we are incrementing the bits, or I should say we're turning on a bit based on the I in the for loop, and then we clear all those bits and then set the new bit so that just one LED is turning on, and then we just change direction once we get to the complete end of that bit set. Works pretty slick. Yeah, I'm impressed. Very good. Well, that's it for this lesson. I hope you've enjoyed learning a little about the 74HC595 shift register and how you can increase the number of output pins to your Arduino projects. If you like this sketch, be sure to let me know in the comments section below. I'll have additional links for other interesting videos and code for this project in the show notes below. Join me next time for lesson 25, the serial monitor. We've used that before. And if you like this video, give it a big thumbs up and subscribe. Thanks, and see you next time.